Hello everyone and welcome to EET1021. This lecture is on chapter 21, Inductive Circuit. Topics that will be covered in this chapter will be the sine wave for the inductive current and voltages. So we will see that the current in an inductor lags the voltage by 90 degrees. We will also analyze inductive reactance and resistance in series. In section 21.3, we will deal with impedance and the impedance triangle. We will also cover the topic of reactance, inductive reactance and resistance in parallel, as well as the quality of a coil, and AF and RF chokes, and the general case of inductive voltage. Alright, so let's start with the sine wave, in which the current lags the voltage by 90 degrees. So when the sine wave variations of current produce an induced voltage, the current lags its induced voltage by exactly 90 degrees. So when we have basically an inductor connected to a applied voltage, okay, the change in current through the inductor generates an induced voltage, okay, and these current and voltage are 90 degrees out of phase. It's very similar to the situation we experienced when we study capacitors, except that in the capacitors the current led the voltage by 90 degrees. In this case, the current is going to lag the voltage. In other words, the voltage is leading the current in inductors. So the phase angle of an inductive circuit is 90 degrees because the inductive voltage depends on the rate of change of the inductive current. So the current wave does not have its positive peak until 90 degrees after the voltage wave. So therefore, the current lags the voltage by 90 degrees in a inductor. Okay, but just like in capacitor, they are 90 degrees out of phase, but the frequency must be the same in both cases. So the voltage and the current must have the same frequency. So when a coil has a series resistance, the current is limited by both the inductive reactance and the resistance. Because remember, the resistance is opposition to current, and the reactance is the equivalent to resistance in an inductor. Okay, so resistance and inductive reactance, they both measure in ohms, so therefore they both represent opposition to current. Okay, so they limit the current. So the current is the same if we are dealing with a series circuit. Okay, so the current is the same through the inductor as it is through the resistor. And each one of them has their own voltage drop. In other words, we have some voltage drops across the resistor, and there will be some voltage drop across the inductors as well. Here is an example of a series circuit. Okay, we have the total voltage of 141 volts. We have a resistor of 100 ohms in series with an inductor that has a inductive reactance of 100 ohms. So this current, the current in the circuit, because it's a series circuit, there is only one path of the current, so the current should be the same all around the circuit. So every component has the same current going through it. Okay. However, the voltages across the different components, the resistor and the inductor in this case, the voltage is 90 degrees out of phase. Okay. So therefore, if we need to add voltages So we have 141 voltage applied, but then we see that if the current is 1 amp, for example, so 1 amp times 100 ohms, that gives you 100 volts across the resistor, and the 1 times 100 gives you 100 ohms across the inductor. However, if we add 100 plus 100, that should be 200 and not 141, right? So that would be the case if they both were resistors, for example. But remember that the current times the resistance gives you a voltage on the resistor, and the current times the inductive reactance gives you a voltage on the inductor. But the voltages across the resistors and the inductor are 90 degrees out of phase. So therefore, to calculate this voltage, we cannot just add 100 plus 100. We have to do we have to take in consideration the 90 degrees out of phase, like it is right here. So in order to calculate the total voltage, we have to use the triangle, the Pythagorean theorem. Okay, let's look at the waves right here. The current is the same, right, for the whole circuit. So here is the waveform for the current. Okay, one cycle takes 160 degrees, and then the maximum is at 90 degrees, back to 0. Then the minimum is at 270 degrees, and then go back to 0 at 360. All right, so the current and the voltage on the resistor are always in phase. So this one has the same phase. See, they go through zeros, and their maximum values at the same time. This is the voltage on the resistor, and this is the current on the circuit. So, however, the voltage on the inductor, L, is ahead of the current by 90 degrees. So in other words, it gets to the peak value 90 degrees before the current or the voltage on the resistor gets it. Okay, so this one is ahead or leading. The voltage leads the current by 90 degrees, and here is the waveform for the voltage on the inductor. So if we add this voltage plus this voltage, we will get this other form right here. Okay, this waveform, this is the waveform for the total voltage. When we add these two, that one plus this one will give you this one right here. Okay, as you can see, it is out of phase with the current, but the frequency is the same. In other words, the frequency means that this one has only one cycle. This is one cycle right here. Here's the one cycle on the same period of time. Okay, so when it comes to add the voltages on a series on a RL series circuit, we're gonna have the voltage on the inductor leading the voltage on the resistor. Okay, because remember, the voltage always lead the current. Okay, and the current is always in phase with the voltage on the resistor. So this is the same 0 degree, and that will be 90 degrees right here. So to calculate the total voltage on the series RL circuit, we're going to use the phasors. We're going to add this phasor plus this phasor, and that will give us this amount right here. That would be the that is the total voltage. Okay, same deal, same thing that we did with capacitors, because the voltage on the resistors and the voltage on the inductor are 90 degrees out of phase, so we cannot add it like algebra. Okay, arithmetically we cannot do 100 plus 100, so we need to take in consideration the 90 degrees phase angle. So therefore, if I want to add this vector plus this vector, I need to go from this point to that point. Okay, and using this formula, the total voltage equals the square root of VR squared plus VL squared. Same for the impedance. When we have impedance in a circuit like this one, for example, we have a resistance and we have a reactance. So remember that resistance and reactance are 90 degrees out of phase. Okay, so if we wanted to find what is the total impedance, remember the total impedance means the total opposition to current, and we call it impedance because the opposition to current from the inductor is the reactance, and the opposition to current from the resistor is the resistance. So a general word for the whole for the total opposition to current would be the impedance, and it's represented with the letter Z. Okay, so the total impedance would be the square root of R squared plus XL squared. Okay, which is, this is R, this is XL, so this right here is the sum of these two phasors, and that would be, in this case, would be 141 ohms. Alright, so the phase angle in the series RL circuit, which stands for R for resistor, L for the inductance. If you have this in series, let's see, the total impedance will be the reactance plus the resistance with the 90 degrees phase angle. Okay, when we add these two together, this is what we get. In this case, we have 40 plus 30 equals 50 because of the angle. So that would be the square root of 30 squared plus this plus 40 squared. That will give you a total of 50. So in here we have a resistance of 30 ohms, a reactance of 40 ohms, but the total impedance would be 50 ohms. Okay. And this angle right here, the angle between the total impedance and the resistance, if we use the resistance as a base, then the angle theta can be calculated by calculating the tangent inverse of theta would be the opposite side, which is this one, which is the same as that one, divided by the adjacent side, which is 30. So in this case would be 30 divided by 40 divided by 30 equals 53 degrees. So this theta angle is 53 degrees. What that means is that the voltage applied, the total voltage, is leading the current by 53 degrees. Okay, very similar to the case that we have when we deal with capacitors. Now, what happens when they are in parallel? Okay, so the current in parallel, we will have the same situation that we have when we deal with the regular purely resistive circuits. Okay, we have a total current that comes in here, and then some is going to go this way and some is going to continue this way. Okay, so the total current would be the sum of the two currents, the current that goes through the resistor plus the current that goes through the capacitor. However, remember that these currents are 90 degrees out of phase. Okay, so this is the current for the resistor, and remember that the current is lagging the voltage. Okay, and the resistor, the current on the resistor is always in phase with the voltage. So that means the current on the inductor lags the current on the resistor, right? So in here we have IL and IR, but in order for us to add these two phases, we have to use the Pythagorean theorem again. Okay, so that would be the square root of IR squared plus IL squared, and that will give you, in this case, 5 amps, because we have a total of, let's see, these two components are in parallel, right? The resistor and the inductor, they're in parallel. So therefore, the voltage applied to the resistor is the same voltage applied to the inductor, right? Because they're in parallel. So if I know the voltage here, which is 120, divide that by 30, that will give me the resistance current of 4 amps. If the 120 volts are divided by the 40 ohms in the inductor, that will give me the current in the inductor of 3 amps. Okay, but 4 plus 3 is 7, not 5. just remember that we cannot add this current plus this current arithmetically, okay? So we have to use the Pythagorean theorem in order to sum these two because of the 90 degrees phase angle. So that would be 4 squared plus 3 squared equals 25, and the square root of 25 equals 5 amp. Okay, as you can see, we have a total current that comes in 5 amp, but then we have 4 goes this way and 3 goes this way. 4 plus 3 is now 5. However, if we add them as phasor, yes, it is 5. So the phase angle in parallel is the same thing. We're going to have the current, and we're going to calculate this angle right here. We always take the current on the resistor as base, okay, because that's the one that is in series, is in phase with the voltage. Okay, so what's this angle? Well, it's the inverse tangent of the opposite divided by the adjacent. Okay, so in this case would be the opposite would be this right here, which is the same as this one right here, right? So that would be the current divided by the current on the inductor divided by the current on the resistor. It would be 3/4. Okay, it's negative because I'm going down. Okay, from here go down, so this value is going to be negative. So therefore, the angle, it says, is negative 37 degrees if we take in the resistor as a reference. Okay, it goes down this way, so that's why the angle is negative. But this just means that the total current lags the source voltage by 37 degrees. This current right here lags this voltage, okay, by 37 degrees. Okay, so this is the same thing, okay, to calculate the total current when we have the current on the resistor and the current on the inductor. So we have to use the Pythagorean theorem, okay, because we cannot add algebraically. We cannot add 10 plus 10. We have to do it like adding phasors or vectors, okay, and that would be the distance that is equivalent to this current plus this other current. Okay. Now the impedance, the total impedance on the RL circuit that is in parallel resistance with inductors. Okay, we know that the resistor has resistance. The resistor has resistance, and the inductors, they have reactance. Okay, so the total equivalent impedance for this type of circuit will be better calculated easier to calculate if we calculate the voltage and the total resistance. The total current. Okay, because remember the opposition to current is equals to the voltage divided by the current. So if we divide the total voltage divided by the total current, that will give me 24 ohms. That is the total impedance for this parallel circuit. Okay, we have 30 ohms here, 40 ohms here, but the total must be, the equivalent must be less than the smallest one. So this is 30, so this is 24. We're good. Okay, so the easiest way to calculate the impedance on a parallel circuit is by calculating the total current first, and then divide the voltage by that total current. That will give you the total impedance. Okay, remember also that in parallel, if that was a purely resistive circuit, it would be like this: R1 times R2, okay, divided by R1 plus R2. Okay, oops, there you go. However, in this case, we can replace R2 with the XL, so we can say that it would be R1, okay, or just R. Let's say just R. Okay, just R times XL, all right? And then in here I'm gonna add R plus XL. So remember that this cannot be just done like this, because I cannot add R plus XL because this is resistance, this is reactance. They're 90 degrees out of phase. So in order for me to add let's say R and XL, I need to find this distance, and that would be the resultant. Okay, so to do that, so I will have to take the square root of this square plus that square. Okay, so that will be the equivalent resistance, not resistance, but the equivalent impedance for this parallel circuit. That would be the other way of doing it. But if you know the total voltage and the total current, just divide the voltage by the current, and that will give you the impedance. That will be quicker if you know these values. Okay, these two values, I and V. So in a parallel circuit with inductance and resistance, the parallel branch currents IR and IL have individual values that are 90 degrees out of phase. Okay, and the IR will lead the IL. So IR and IL are added by phasors to equals the total current, okay, which is the main line current. So basically, do not add this algebraically, okay? Just do it like phasors using the Pythagorean theorem. So the negative phase angle, negative theta, is between the line current T, IT, and the common parallel voltage VA. Okay. So because the current lacks the voltage, that's why the angle is basically like that, clockwise. It's negative angle. Okay, just because the current lacks the voltage. And the voltage, basically, we take that as a reference, then the current will go down. So it will be like this. That's the voltage, and then this will be the current. Okay, so therefore, whatever angle we get from here is going to go in this direction. That's why it's negative. But it's nothing than just saying that this is the angle that these two items are out of phase. So then remember that the less parallel inductive reactance allows more current, because the reactance is the opposition to current. Remember, so the less reactance, then the more current, to make the circuit more inductive. So with a large negative phase angle for IT with respect to VA. Okay, so basically the smaller the reactance, the more inductive that the circuit becomes. So the ability of a coil to produce self-induced voltage is indicated by the reactance. Okay, so in other words, the reactance determines how much voltage this coil can induce, since it is a factor of frequency and the inductance. Okay, so the frequency, the inductance, the current determine the induced voltage. And another current itself. Remember, the current, the induced voltage depends more in the rate of change of the current itself. A coil, however, has internal resistance equals to the resistance of the wires in the coil. Okay, so no wire is perfect. No wire is this will only happen with the ideal wire that has no resistance. So every wire has a little bit of resistance in it. So this internal resistance, we can call that Ri of the coil, reduces the current, because it's a resistance. So resistance is in opposition to current, which means less ability to produce induced voltage. So combining these two factors of the inductive reactance and the resistance in the coil, they say the quality of a coil is Q equals the reactance divided by the internal resistance of the coil of the wire. Okay, so this is a symbolic for the it's a symbol for the for an inductor, right? So the inductors have the reactance, but the wire also has its own resistance. Okay, so that's very small though. Okay, so the quality of the quality of the coil will be based on the reactance divided by the internal resistance of the wire that the coil is made out of. All right, so let's take a look at this this circuit right here. We have a reactance of 1,000 ohms, we have a resistance of 100 ohms, and the applied voltage, total voltage is 100 volts. Of 100 volts, okay? So if we calculate the voltages across these different components, so these 100 volts will be distributed as 99.5 here and 9.95 through here. Okay, so this voltage here on A is the voltage that goes out. So L has a practically all the voltage drop with very little of VT across R. Okay, in this case, just look at it and we can see that the inductor has 10 times more ohms than the resistor. So we can see that the reactance is much greater than the resistance of the frequency of the AC source voltage. So the inductance here is used as a choke to prevent the AC signal from developing any appreciable outputs across R at the frequency of the source. Alright, so with this we conclude the chapter 21. Please do the problems at the end of the chapter for practice. And thank you for your attention and the opportunity to serve you.